I'm Olivier Crémeux. I'm the local head for food for Stäubli Robotics North America.
And I'm Anthony Romeo. I'm a product marketing manager for Oxipital AI. So Oxipital AI spun out of Soft Robotics. We really decided to focus on the machine vision, AI-enabled vision side of things. We have a primary focus in the food space. The reason being is that food really lends itself to AI-enabled vision. There's no CAD file for a chicken wing. It's non-repeatable and really lends itself to AI-enabled vision.
And just a few words about Stäubli Robotics. We are a Swiss family-owned company, mechatronics solution provider, 134 years old, and working in different activities, textile, connectors, and robotics. Robotics has been our passion for over 40 years now, so you have a quick look at the development we've done. Our particularity is that we develop our own 6-axis kinematic, our SCARA 4-axis kinematic, and for the last 6-7 years, we have developed our range of HGVs. We worked, now it has been nearly 20 years in the food industry, and especially in primary environments. So on our side, we have a clear understanding of the challenges that you see in food for robotics, which are mainly the humidity, meaning developing a solution fully waterproof, the bacteria risk, and the cleanability, the wash down that you require on the equipment, the evolution of chemicals that are used in the plants, and the actual chemical compatibility your equipment need to have, and also the change of temperatures. For that, we developed a specific range. It's our food grade range called HE Robots. If you have more information, we can go over this more in detail later on. When we talk food primary, we look at specific market segment. Definitely, and that's why we are here at IPPE, meat processing is a big one. A lot of potentials, a lot of type of applications we can address with robots. Dairy, convenience food, and bakery are also really important market. In the video, you see a couple application example of what we currently do in terms of robotic application in food primary, meaning direct contact with a fresh product. When we talk food primary environment applications, there are key elements to consider for actual successful integration. You do want to have a reliable equipment that can fit in the environment, that can withstand the environment. You also need to have an equipment that is easy to clean, easy to maintain. That's a priority one in food. When we talk food project in or robotics, of course, it's linked to high speed and conveyor tracking most of the time. That is involving vision, and you need to have a technology that is capable to address this. And when we talk vision, of course, one of the big trends and huge point of interest is AI and vision, and that's why we are doing this presentation with Oxipital today.
So I think there have been a couple reasons why AI-enabled vision hasn't gotten a ton of adoption and a couple pain points that prevent people from using AI-enabled vision. Number one is just training the model for the system to work. Typically what will happen is you'll mount a camera in the production environment, you'll take a whole bunch of images, and then some unlucky soul has to go and label those images, say this one's good, this one's bad. It's very time consuming. I've heard companies that hire a team of people full-time just to label images. There's also a lack of application control where once the model is working, there might need to be a little slight tweak, but the only way to make that slight tweak is to retrain the entire model, which is very error prone again and very time consuming. And then once you're in production and everything's working and the AI system is doing great, how much money is it actually saving you? Did it cost you money to set this up? Being able to understand how much money an AI vision system is saving you is also very important. So AI has come a long way, and what can we do with it today? So instead of labeling hundreds of thousands of images, we can take a full 3D scan of a product that we're going to be inspecting. So this allows us to marry the 2D and 3D data together and get a really good, deep object understanding of what we're scanning. So we know all of the dimensions, we know how wide it is, how long it is, we know areas that might have defect, and we know the area and volume of those areas. With this deep object understanding in 3D scans, we can use synthetic data generation to train our model instead of traditional labeling. So here we scanned a bunch of different pieces of chicken and we said, let's drop these pieces of chicken on a blue conveyor belt and let's drop 5 pieces of chicken from our library of 30 that we've scanned. And let's do this again and again and again, hundreds of thousands of times. Instead of a person having to label this, because we're synthetically generating this, we know the exact area, volume, location, everything there is to know about these pieces of chicken without having a human to go in and label it. So it eliminates a lot of the error proneness of traditional labeling. And this allows us to generate pre-trained object models. So instead of a customer going and saying, hey, I want to buy your vision system, I also need to hire an application engineer to train the system, I also need to hire a training for my team, so once it's good, we're good to go. Nope, we do all the training in-house. We can create an object model, and the customer would say, I want to buy an object model that looks at chicken, inspects the fat level, and determines the orientation. So with these object models, we can take into account things like defects, and we can train for different types of defects. Here we can see one piece of chicken is 180 degrees the wrong way. We're seeing the membrane side. The other one is flipped and not packed. It's occluding the other piece of chicken. These might have different root causes, and being able to identify these defects is important to address the root cause there. We can also determine pick priority and have the robot prioritize certain things. Maybe it wants to grab the largest piece of chicken first. Maybe it wants to grab some with the highest fat content first. Maybe you want to grab some that are all on the left side of the belt because that arm is closer to that side and it can increase your pick rate. And then once we're in production, we can see some of these analytics. So being able to see here, oh, we had 1,692 pieces with low trim. How much money would that have been if we correctly cut those? How frequently do I need to change the saw blade to make sure we're not getting these low trim things? It's really important knowing not just product is good and bad, but why it's bad, which allows you to go fix the root cause. So with these models, what does it allow us to do? We can implement things like intelligent gripping. So here you can see if we were picking these apples and we sent the pick coordinates to the robot and we had a little circular gripper, 2 of these fingers would be jamming into the neighboring apples and might bruise them. Not good. Instead, we can alter the pick position so that we're avoiding these collisions, so we're not damaging neighboring product. We can also determine defects. Here, we might want to pick out the ones with the muscle side and ignore the ones with the membrane side, let those go. Again, understanding different defects allows you to take action to prevent bad stuff from going to the customer. We can also look at subcomponents of different parts. Here we can see we're identifying where there's fat on the meat. Understanding these subcomponents, again, allow you to make more informed decisions and fix upstream equipment that might be getting damaged when we see lots of fat coming through here. Again, because we're using an AI-enabled solution, there's no CAD file for chicken wings. Everyone's going to be a little bit different. So in the models, we bake in a lot of organic variation that allows us to have different sizes, different shapes. If one year all the birds are a little bit smaller, not a problem. We also can handle chaotic infeed. I know a lot of automation projects require things to be either justified or indexed. For us, it doesn't matter. Stuff can be piled. We're imaging directly in the robot pick area, which allows us to pick things from a pile, get the next thing underneath, and account for movement in the robot pick area. So here we can see we're going to pick up one Capri Sun, but the neighboring Capri Sun, it moves a ton. If you were to image upstream, you wouldn't be able to account for that movement. Because we're looking right in the robot pick area and handling it in real time, we can account for that movement and get the right pick coordinates to go back and pick it once it stopped moving. Again, we can optimize robots with different pick priorities. Maybe if you have 6 robots that are picking things from a pile, the furthest one's downstream, you want to make sure you don't miss any product. So you would prioritize getting stuff that's going to go off the belt. Maybe upstream, you want to prioritize the robots on the left, get stuff on the left side of the conveyor, on the right side of the conveyor, so the arm is moving less time, so you can optimize picks per minute. We also can bake into our models things like lighting variability. A lot of vision applications, if the lighting changes, you're almost back at square one and need to completely retrain, reset everything up. Again, because we're using synthetic data generation, we can simulate different lighting environments when we're doing that training. And that allows us to have much quicker iteration. If a customer wants a new defect in, we can use the existing model and bake in the new defect. If there's ever a retrofit and you switch from a blue conveyor to a white conveyor, a lot of existing systems, you'd have to restart the training, start getting those images, start labeling again. For us, we can just run that synthetic generation with a different conveyor background.
When you talk food applications with robotics, speed is critical. The throughput is always a key question, an element we need to analyze with our technical team, and basically what the customer is looking for to justify his ROI. But a robot can go fast. The problem in food is you have so much variability on the product, and that's the enemy of fast for robotics, because robotics is really repeatable. So the key to really optimize your actual application performance is by feeding the robot with the correct information, the product detection with the correct additional, let's say, parameters that you can send to the robot to anticipate the next move, basically. Yep. So definitely interesting, and thank you, Anthony, for sharing this. Now the question is, how do you combine AI vision and robotics? And what you described, what I can talk about on the robotic side, you can feel like, okay, this is going to be really complex. There is a lot of things in play, from the actual conveying system, the vision input, the robot, the actual tooling, all those things together. But what we have been working on with Oxipital is to try to develop it as a turnkey solution. So on one side, you teach your model learning on the vision to facilitate the actual product detection. And then you have a simple Ethernet communication that goes to your vision processing unit that will allow this model learning and evaluation of the product and actual send the robot positions you need to go to. So an additional Ethernet communication to the robot. And on the robot side, there is a lot of going on that you don't have to be worried or taking care of, because in our controller, we'll take care of the path planning and the actual servoing, friction management of all the axes to do the actual optimized motion at the speed that you want. So at the end, it's really learning the product, adding the AI to it, anticipating the variability of the product, and sending what you can detect and anticipate through the AI to the robot as a position command that he will go to.
So here we can see a system that we have that's using occipital vision and Stäubli picking. So this first part, we have oriented chicken breasts on a conveyor belt that we're tray packing. This next part, all of these chickens are in bulk, and we're able to, again, identify which ones to pick up from the bulk and singulate them. Once they're singulated, we can determine the orientation to see if it's muscle up or membrane up. And then again, once it's the right orientation there, we can tray pack it, alternating. This is something what you would see in the supermarket, right? And so again, it seems really daunting to get started with AI vision. Really for us, it's pretty simple. We have a very short 1, maybe 2-page requirements document that just lets us understand a little bit about your application. The more that we know going in, the quicker we can get a viable model early, and gives us more time to make it even better and iterate on it.
Yeah, and on the robot side, a lot of time customer comes to us and they have a process they want to automatize, and they are not clear on, okay, what are the good step, the proper process to go through. So here are quick notes that I want to highlight, and how we can help customer to develop their project and make sure from the concept to the actual SAT and production, everything goes well. So first step that you want to do is start with 3D simulation and concept validation. This is a support that us, robotic company, we provide to you. We can go over your actual layout. We can go with the machine builder over the actual cell design and validate that, okay, reach, robot positioning, footprint, risk of collision, all this will be anticipated. Then for that, we also need to have a clear idea of your process sequence, and we can help you optimize this sequence. When you automatize, the goal is to use the robot for its performance. You don't want a robot that is waiting for a process and have, like, in his sequence a lot of delays. So we'll look at this, and then, of course, to optimize the throughput, the peak per minute that you will get with the robot, typically, then we'll look at, okay, actual speed of the robot, trajectory, potential blending on the trajectory, and then limit of inertia, because when we talk food, the tooling is really important. The tooling can become really complex, and so you can look at dimensions or weights that can be significant and that can impact the actual performance of the art. So all this can be anticipated at the early stage of the project, and it's really just technical evaluation. Then, when you get a little bit further in the project, validated the tool design and confirming the actual performance that you anticipated at the simulation level is really important. For that, We can go more in depth with motion descriptors, adjustments, finalizing, fine-tuning the trajectories when you have the final tooling. And then we can optimize also the delays if it's a mechanical gripper, if it's a vacuum, all those times where basically you have to wait for the tooling to do something, then we can anticipate and we can try to optimize it. When we talk food, the reality is simulation is a good help, but reality is always a little bit different. So recommendation and what we try to put in place is real test with real product. And during those real tests, we really validate and help the machine builder to finalize its proof of concept and to be in line with the specs of the projects. So that's typically the three main guidelines I see for food projects that you need to follow if you really want to be successful. Quick summary of what we discussed, Anthony, today. Talking about AI and robotics. Or maybe you want to talk about the AI part?
Yep. So I think really the key takeaways on AI is that if you've tried AI-enabled vision in the past, I think moving forward, there's different solutions out there. And it's easier than ever to get started, and it's easier than ever to communicate with robots when using AI as well.
Yeah, and on the robot side of things, I would say really important is that today we have developed plug-and-play solution with vision and AI system like Oxipital. So we really are able to address better this variability on the product side of things linked to fresh product and food. And then on the robotic side, what you really want to do is evaluate the actual environment compatibility and the technical aspect of the product. Food projects are not always simple. There's high-speed requirements and potential complex motion to handle. And that's where you need to follow the actual steps for a successful project and work with us to help you through this.
V-CORTX by Oxipital AI. AI vision for the ones who make things happen.